In this video, I want to talk about the synchronous logic design and some of the rules that we must follow for the design that we make for synchronous logic circuits. So if you remember from before, I said that sequential logic circuits are circuits that have memory. So that means that for any output that we get at any given time, that output is dependent on the current inputs of the circuit and also the previous state of the circuit. So generally speaking, sequential circuits can be considered as all the circuits that aren't combinational. But having this very broad definition does not help in designing such circuit. So let's take a look at this very simple circuit that we have here. We have three inverters that are connected back to back, and we have named these three nodes, basically the input of the first inverter as X, the input of the second one as Y, the input of the third one as Z. And as you can see, the output of the first inverter is connected to the input of the second one, or the output of the second inverter is connected to the input of the third one, and finally the output of the third one is connected to the input of the first inverter. So now if I want to draw the timing diagram for this circuit, I assume that at time 0 nanosecond, as we have here, the value for X is changing from 0 to 1. So let's just see what happens for the rest of the inverters. So for this inverter, when we change the X from 0 to 1, the output of the inverter changes from 1 to 0 after, you might say, a few nanoseconds of delay. So we have the output to go from 1 to 0. So the input, the value for Y changes from 1 to 0. That makes its output, which is Z, to change from 0 to 1 after a few nanoseconds too. So we have this changing from 0 to 1. So now when Z changes from 0 to 1, its output, which is X, is changing from 1 to 0. So because of this, we have X changing from 1 to 0. So now X changing from 1 to 0 causes Y to change from 0 to 1. So after a few nanoseconds, you might say, we have Y changing from 0 to 1. This change triggers X to change from 1 to 0. So we have this thing changing Z from 1 to 0. And then you can see that this procedure is present indefinitely. So at first X changes from 0 to 1, that makes Y change from 1 to 0, that makes Z change from 0 to 1, that makes X change from 1 to 0, and then this process is repeated indefinitely. So that's an example of an A-stable circuit. So if you remember, when we were talking about the bistable circuit, we only had two inverters that were connected back to back. And we said because of this design, in whatever state this circuit is, the two possible states, it remains at those states indefinitely. But here, since we have three inverters back to back, we don't have a stable state. In fact, our circuit is A-stable. That means that X, Y, and Z are basically switching back and forth between 1 and 0 indefinitely. So that is what we call as an A-stable circuit. In fact, any circuit like this that has an even number of inverters to be connected back to back is a stable circuit, but any circuit that has an odd number of inverters is an astable circuit. So keep that distinction in mind. But now the question becomes, how can we control such a circuit? Because the period or the duration of, let's say, x being 1, do we have any control over it or not? So this period, this duration, is usually affected by all the internal parameters of the inverter themselves. So depending on how much delay that we have here, this thing would change. Depending on the temperature of the circuits themselves, these delays would change, and we have a different time frame for when x, y, and z change from 0 to 1. You remember from before when we talked about the timing of the combinational circuit, we said that there is a minimum and there is a maximum for the delay for any individual gate, and we usually don't have control over the exact amount of delay. What we know is basically a range. So because of that, controlling such a circuit is very hard. So in this circuit we don't have any inputs, but we have 3 outputs. So you can say x is one of the outputs, y is the second one, and z is the third one, right? But we don't have any inputs, so we don't have any control over how these values change. Also, this circuit is an astable circuit because it oscillates, its outputs oscillate between 0 and 1 indefinitely. And the period for this oscillation depends on the inverter's delay. So again, since the delays for the gates, we don't have any control over the exact amount of delay, all we know is a range of possible delays. We basically cannot control the period of this oscillation either. So this circuit we say to have a cyclic path because all the components are within a loop. So as you can see, if I start from this point, I go through all these components one by one, I end up at the same place. So that is what is called a cyclic path, which means that the output of the circuit is fed back to the input. So clearly, based on this example, you see that having such a circuit, we have little control over the aspects of the circuit. So we need to come up with some rules in order to be able to control this type of circuit. And the same way that we started with the state element, we started with the bistable circuit, and we realized that that is not good enough, and then we move forward with the further design. We started from the bistable circuit, we went to the SR latch, we went to the D latch, and then finally we ended up at the design of the D flip-flop, and we said that D flip-flop is the most preferred state element because not only it gives us the access to the time at which we want to store a data or like one bit of a state in the flip-flop, but also there was a separation between the time that we stored the data and also the data that we wanted to store as well. And finally, that process of storing the state would happen at, you can say, practically at an instant. So now that we have this, we can combine all this knowledge from before. So we come up with a set of rules that are governing the synchronous sequential logic design. So the first rule that we have is that we have to break all the cyclic path in the circuit by inserting registers or flip-flops. So any cyclic path that we have in the circuit, in order for that circuit to be considered a synchronous sequential circuit, it needs to contain a flip-flop. Without that, it is an example of an asynchronous logic circuit. So that is a very important thing that we need to consider. Another rule that we knew it from before is that registers are there to contain or store the state of the system. So this is not something new. We actually designed the state elements to be able to store the state of a system. The third rule states that state changes only at the clock edges. So that means that the system is synchronized to the clock. And that is basically the reasoning behind calling these type of circuits synchronous, right? Because the act of storing the state of the system happens at the clock edge for all the registers and flip-flops in the circuit. So because of that, we say that the system is synchronized to the clock. So now that we have this, let's just go over these follow-up rules that says every circuit element is either a register in a sequential logic circuit or is a combinational circuit. So this combinational circuit can be anything from a simple element, let's say one single gate, or to a more complex combinational circuit. So we either have a register in the circuit, right? So all the elements that you find in this type of circuit, the synchronous sequential circuit, is either a register or flip-flop or a combinational element or circuit. The second follow-up rule is that at least one circuit element is a register. So if we don't have any register in our circuit, it definitely is not a synchronous sequential circuit. It can be a sequential circuit, but it is not synchronous, it's an asynchronous. Because we need registers and flip-flops to basically sync everything with the edge of the clock. This is very important. So inclusion of registers and flip-flops basically helps us to synchronize everything with the clock edge. The third follow-up rule is that all the registers must receive the exact same clock signal. So everything in the circuit, basically every state restoration happens on the edge of the clock. And then finally, and this is something that we realized from analyzing the previous example, and we actually had it here too, every cyclic path must contain at least one register. So it can have multiple registers, and that is something that we will later on talk about, but it needs to have at least one register. And that is true for every cyclic path. So if you have any loop in your circuit, you need to have a register. Otherwise, that circuit is not considered a synchronous sequential circuit. So there are two common synchronous sequential circuits that we will talk about in the following videos. The first one is what is called the finite state machine. And the third one is pipelines. So we will go over these two types of sequential circuits in the follow-up videos.